I'll restart. Is the recording started?
Yes.
Okay. Hello, everybody. Today we're going to be presenting our capstone presentation, the Prosthetic Drone Unit, or as we like to call it, the PDU for short. A quick outline before we begin. We're going to be talking about the purpose of our project, its global impact and its related works, the design requirements and specifications, its related theory, the project schedule and summary of significant progress, conclusion and finalized plans. A quick overview of the team members. On the softer side of things, we have myself and Subhash Limbu. I am the team leader. My name is Michael Cali, and I'm in electrical engineering. And my role was to implement the software as well as some 3D modeling as well. On the other side, we have Subhash Limbu, who was my teammate, in which we worked on 3D modeling and software. On the hardware side, we have Dean Riccio and Ifanio Bikwe. They're both electrical engineers, and their role was to prepare the hardware design and PCB design, as well as 3D modeling for the project. So the main objective of our project is to implement a wireless communication technology between two printed circuit boards and to operate and control a prosthetic hand. We were also driven to create a cost-effective alternative in this growing industry.
As you can see in the image, this is the first 3D printed robo hand and prosthetic hand created by Richard Van and Ivan Oven. There are mainly 5 types of prosthetic grippers, as you can see on the image, starting from top right: passive prosthetic hand, body-powered prosthetic hand, Mayo electric prosthetic, hybrid prosthetic, and activity-specific prosthetic. This is a quick outlook on the history of prosthetic gripper, invented throughout the time from early Renaissance to the 21st century. Our system aims to achieve a step closer to cheaper and efficient prosthetic, making a positive impact in the society.
So a quick overview of the design module specification. We have the person flexes their fingers. So the ESP32 checks for a change in flex sensor position. If it does detect a servo position change, then it sends that information over to an ESP32 on the other side of the project, on the claw side. And when the claw receives that wireless data from the sensor on the glove, it sends the data to the microcontroller that is on the claw gripper and controls the servo motor angle and opens and closes the prosthetic hand that we had created.
For the marketing requirements, we surveyed the general public to identify the needs to be satisfied, as well as the justification for each marketing requirement. And an engineering requirement was chosen with respect to that, to each individual marketing objective in order to achieve them. We compared the marketing and engineering requirements to view the respective relationships between each one of them, and we found that decreasing weight, for example, would result in positive correlation to an increase in mobility. After determining the engineering and marketing requirements in the previous slide, we decided to use the following metric, the needs identification, to geometrically weigh the importance of each attribute determined in order to tailor our project design towards the scaled metric. The objective tree constructed, as you can see on the slide, gives a detailed description of what would be needed, as well as the weight and importance of each needs identification.
So for the system description in terms of hardware for the prosthetic hand that me and Gerald worked on, this involved a microcontroller, a charging IC, a protection IC, a boost converter, ESD protection for the USBs, a flex sensor connector, an ESP32 connector, along with the servo connector. Here's the control unit schematic, or the actuator, which is the servo PCB. The way that it works is you have a 3.7 LiPo battery, which powers the microcontroller, ESP32, and input of the boost converter. The DC to DC boost converter then outputs 5 volts directly to the servo motor, in which the servo motor rotates depending on the angle and position of the flux sensors. Here you have the control unit schematic for the flex sensor PCB. This is very similar to the servo PCB with the exception of the boost converter, seeing as the flex sensors and ESP32s only need 3 volts to operate. So you have a 3.7 volt LiPo battery, a switch. Once that switch is flipped on, it then powers the flex sensors and ESP32. So these are the 2 boards that me and Gerald designed through a PCB software known as KiCad, in which we placed footprints and each trace individually to make sure that we could create the best board layout possible.
For the related three, we considered the boost converter as one of our selected microelectronic components on the schematic that you saw earlier. We decided to use this to boost our supply voltage, which was a lithium polymer battery from 3.7 volts to about 5 volts. To achieve this, we took into consideration some of the consumption of the electric components we're going to be using, such as the motor and some of the fundamental circuit network concepts that we learned earlier, such as Kirchhoff's current law and total runtime of our device. Considering the battery capacity is about 600 milliamp hour, with the servo motor operating at 500 milliamps, this would give us a runtime of about 2 hours.
So these are some of the technical specifications that were involved with the flex sensor PCB. We got both boards fabricated by a PCB manufacturer known as JLC PCB. Some of the specifications include the dimension, the board thickness, if there is any impedance, along the materials used to fabricate the board. Here's the technical specifications for the servo PCB. It is very similar to the flex sensor PCB with the exception of it being 4 layers, having different dimensions along with an impedance that was required so that we could directly load the microcontroller that was on the board. Here are some of the features of the microelectronic components that we used on both of our PCBs. We wanted to make sure that every component that we used would essentially create a unified system. And for instance, the charging IC that I selected has a programmable charge current from 15 milliamps to 500 milliamps. This is very important because if you want to charge the battery at a faster rate, then if you set the charge current to a higher value, it will take less time to charge the battery overall. Here's a continuation of some of the components that we ended up using in both of our schematics. For instance, the MOSFETs that we use for the protection IC has a fast switching speed, which means that if an issue were to occur where the LiPo battery, for whatever reason, discharges or short circuits, that the protection IC can quickly activate so that the battery will not explode or catch on fire.
Here's a flowchart of how the software operates on our boards. So when the ESP32 is first turned on and initializes the Wi-Fi transmitter, it then begins searching for any changes in the flex sensors that we used. If the ESP32s detect any change, the new value is then sent wirelessly to the other ESP32, which is found on the claw gripper, and is then sent to the microcontroller, which then controls the angle of the servo and opens and closes the hand as we require. For the drone implementation, we use the software called Betaflight. Unfortunately, this is the only software that is available for controlling the characteristics of the drone and its flight pattern, as well as the only software available to control the GPS coordinates for autonomous flight.
For the hardware design implementation, this is similar to what I spoke about earlier in terms of the schematic. So for the flex sensor PCB, you have a switch. Once that switch is on, the battery starts sending current throughout the board. This essentially produces a voltage, which then powers the flex sensors in ESP32. The servo PCB is very similar. You have a battery, the switch turns on. This then powers the input of the boost converter, a DC to DC boost converter, which then outputs 5 volts for the servo motor, and through the wireless communication of the 2 ESP32s sending the changes in the flex sensors, this will then determine the amount of degrees that the servo rotates. So here's a picture of the 2 boards that were fabricated by JLC PCB, in which I soldered all of the components on by hand.
For the 3D model, we used a prosthetic hand, and on the top right side we can see the claw portion of the gripper, and it has the cog built in, and it's pretty lightweight and made of readily available materials in the event that it were to break down or through use it were to snap or break off. On the bottom left and the bottom right, we have the bouncing mechanisms which hold the servo and the claws together. For the 3D modeling readjustments, we needed to do some heavy modifications in order to support all of the components that are being used. We had a top plate that needed to be modified, adding holes for mounting brackets and as well as changing sizes a bit. We needed a spacer for the drone attachment, and we needed a landing pillars to compensate the height difference from the claw to the drone being flat on the ground. Here's a photo of what the drone that we are using in our project. It is a 7-inch quadcopter, and it uses 7-inch propellers to lift our payload, which would include the claw gripper and camera for computer vision, and that can be seen on the right side, on the right photo, as well as the algorithm used for computer vision and the claw mounting mechanism. Here's a video demonstration of our claw gripper in action. So there are actually 2 modes to our gripper. There is autonomous as well as manual. In this case, I'll be showing the manual portion where we have our servos connected to our claw, the flex sensors, and opening and closing your hand determines the opening and closing of the gripper. So as you can see, I'm closing my hand now and the gripper closes. I open it up and it opens itself. And all this information is being transmitted wirelessly. And here I'll be operating the hand, showing you that it is capable of picking up objects of different shapes as well.
This is the Raspbian operating system where we use our Raspberry Pi for our object detection with a camera. We were able to SSH through the terminals into the directory. As you can see in the picture, the object detection on the lower right.
For the functional decomposition, we consider the control unit for the sensor portion of our prosthetic hand. Some of the inputs include the flex sensor information that is being sent, and power of about 3.7 volts DC supplied to the microcontroller of the PCB.
This is the black box. Oh.
For the second functional decomposition at level 1, we consider the servo microcontroller module. Some of the inputs include the wireless transmission from the glove towards the microcontroller on the actuator unit, control unit of the PCB, and one of the supply voltages is rated around 5 volts and operating at 500 milliamps.
This is the black box testing we conducted on the system claw exterior part. Made sure all the parts were up to standards and in our appropriate specs. This is the PCB functionality testing with the flex sensor to make sure everything was working and soldered in the right place. These are the activities done throughout the 1-year semester project, and including the winter. This is the fall semester. We were successfully able to breadboard this prototype, work with the PCB, and figure out the 3D models and the parameters and the flex sensor with the servo motor. In the winter session, we were able to solder the PCB, print the 3D, some of the components of 3D models, begin with the drone work. In this semester, we were able to work on the drone, test the semi-autonomous features, and integrate the hand with the drone. These are the costs that were included for the 3D printer, flex sensor, casing for the PCB, screws, and bolts. This is the cost for the drone, including all the frames, cameras, flight controller, video transmitter, motors, and propeller and battery. This is the comparison between the expected and actual costs of the 3D printer, drone parts, and PCB parts. This is the progress we made through the one year project with the PCB sensor and the hand, with the drone flight testing. As engineer, we strive to be professional and follow the IEE standards. And for the constraint, we had the time for the system to be created, and the PCB diagnosis and mainly working virtually was a constraint. As engineer, we are responsible to implement our job in the right time and right place in a professional manner. So we follow the fundamental duties, rules of practice, and with professional obligation.
So for conclusion and future work, mainly what we got accomplished this entire project was having a fully functioning portable prosthetic device. We were also going to include the autonomous flight system for the drone and even zip tied the prosthetic hand onto the drone so that we could essentially pick up objects with it and create a payload system. However, due to the drone getting into an inaccessible area during one of our flight tests with the autonomous system, we were not able to complete this. However, future work can be done so that the system can be integrated into the future. So for the risk analysis and the mitigation process, we had to consider a couple different risks involved when creating this project, such as putting the boards together by hand. If this is done incorrectly, the boards can result in a short circuit and we would have to reorder everything. The 3D printer not being properly calibrated is a big issue, because if the print fails and we have to wait up to several hours just to get that one print finished, integrating the computer vision and payload onto the drone was also an issue at first, seeing as we needed to figure out the best algorithm that we could use from Betaflight. So for the conclusion and finalized plans, we did have initially some plans for our project that we did not get to finish. We wanted to design and 3D print brackets for the PCB in order to cover up some of the wiring that you saw in the demonstration video. We were going to flight test the drone along with and without the servo PCB, which is connected to the prosthetic hand. Unfortunately, we were not able to get this done, along with calculating the payload and applying the algorithm that we're going to use for the autonomous drone, along with object detection that we were able to finish. And these are our references that we use for the project.
Are there any questions?
Thank you so much,
very
Michael,
welcome.
Sabash, Dean, and Ifani. You did a great job. Any questions, guys? Any questions? I think that's all.
Thank you very much, Dr. Wafa, and thank you very much, Dr. Yakos, for attending our presentation.
Thank you.